we will use the first derivative to find input values that are candidates for local and absolute extreme values. So make sure that's in your notes. What we're going to do with those candidates is then we will take these x values, these input values, and put them into f of x, the original function, because maxes and mins are outputs of our original function. And determine which output values, that's what maxes and mins are, we need to answer the question. So that's the process that we're going to use. I've used graphical examples here, but I want you to understand we can do this analytically without even knowing what the function looks like graphically. These points, these input values of interest that we are using the first derivative to find are called critical points. Critical points. Vocabulary you need to know. You have to know what a critical point is. The candidates that are critical points are endpoints, has nothing to do with your derivative. Stationary points. Stationary points are where your derivative equals 0 or is undefined in a certain way. And singular points, which is another undefined for your derivative. This particularly is where your function takes a sharp turn, so your derivative does not exist. This, in particular, is where your function might have a vertical asymptote, or in some way, other than taking a sharp or sudden turn, your derivative does not exist. You also must know this vocabulary. If you are asked what candidates are critical points for your function, you better be able to tell me endpoints, stationary points, and singular points. These are the only places where a function can have an extreme value. That's it. Those are the only candidates where a function can have an extreme value. The function will not have an extreme value any place else. At no other place on the graph of this function besides the endpoints, or where the function takes a sudden turn, or where the derivative equals 0, the function has a horizontal tangent line. Those are the only candidates where extreme values can occur. So when we take our derivative function and explore what's happening on it and find all these critical points, we're guaranteed when we put those x values into our function, we're guaranteed that we have determined every single input value where an extreme value could happen for our function. So, as a clarification point, just because your first derivative equals 0 or even does not exist does not mean that you will have an extreme value. You need to understand that these are candidates where extrema can occur. It doesn't say does occur. Here is an example, a counterexample, to where the first derivative equals 0, but the function does not have a local or absolute extreme value. This function is increasing and then levels off. We are going to find here that the first derivative does indeed equal 0. We are going to find that the function, whatever function this is, does indeed have a horizontal tangent line at whatever this x value is. But we're going to find that the function just continues after that to increase. There's no extreme value there. So what we're using is we're using what's happening to our derivative function on either side of its root or its 0 or its x-intercept. If this is the original function f of x, and I see that f of x has a maximum, I can clearly see this is a maximum value at whatever x value we're talking about in the plane. I know that from what I know about graphs. I'm going to use the attributes of the first derivative to back me up on this, to prove that f does indeed have a maximum. So I'm going to determine that the first derivative equals 0. But more than that, in order for me to say I have an extreme value, I need to determine what the sign of the first derivative is on either side of that root, on either side of that 0. When I determine that my slopes, because that's what the derivative is, when I determine that my slopes change from positive values, everything here has a positive slope, to 0, and then they change to negative values after that, again, the slopes are the outputs of the derivative, then I have determined that my function must have a maximum at this input value. This defines a maximum. Well, it's easy to see graphically, but what if I just gave you a function and you didn't know that the function had a maximum? How could you determine that it did? You would take the function that was given to you, you would find the first derivative, function in x, and you would set it equal to 0. Then you would find all input values for that function that made that a true statement. Those would be part of your critical points. We would also see where the first derivative didn't exist. Then we would do what we did for increasing, decreasing. We would take all of those critical points, how many ever we had, we'll call this critical point 1 and that critical point 2. We would find test points to the left and to the right. This would also have to be less than critical point 2, and that would have to be greater than critical point 2. And we would plug those test values into our derivative function. And if we determined that our derivative function changed sign specifically in such a way that the slopes went from positive to 0 to negative, then this identifies that my function f had at the very least a local max. It may well be the global max. But I'm going to do the test to see. What does this tell me is going on my function at critical point 2? What must be happening there? The slopes are going from negative to 0 to positive. Negative slopes to 0 to positive slopes. This function had, at the very least, a local minimum. So the slope of the tangent line, the derivative, is going to tell us where our specific maxes and mins occur. The critical points are enough to tell us that we have some sort of extreme value, but this test and testing what happens to the positive or negative slopes on your function on either side of the critical point identifies what type of extrema that we're going to have. If our slopes go from negative to 0 to positive, we clearly have a minimum. Now we're going to have to do some further testing to see if it is the absolute minimum. But at the very least, we know we have a local min, and it's based on what's happening to the output of our first derivative. And we can do that by running this test. This table is used to find monotonicity. That's where you saw it before. But we can use the same results to identify extreme values or extrema. That's pretty brilliant. And in this context, this has a name. Drawing our box that we did for monotonicity, labeling it clearly that we're dealing with f prime, and showing that we have identified our critical points, the only candidates in the plane where the function could have an extreme value. Once we determine what's going on with the sign of the outputs of our derivative, we can determine whether we have a max or a min at our critical point value. This is called the first derivative test. Now we have a name for our little box here. This is the first derivative test. It tells us much more than just monotonicity, which is all we've used it for up to this point.